Now we start combining everything into the parallel and series analysis for the circuits. I mean, you're going to find as we go through this, it's essentially everything that you've seen and learned so far, but we're going to apply it by taking series legs and combining them, taking parallel legs and combining them, and then taking the two and combining them together. It's just the same things that you saw when you did it in your 131 course for DC. So as you progress through here, again, it's an idea. The idea here is look at what you've got. Do you have any of the components that you need to convert into reactive, and then do the types of combinations that you've done before. Okay, so a lot of the things that you are going to see, as I said, you're going to apply the way you did in the first couple of sections of this text. So I'm not going to spend a lot of time going through these. Your textbook has these in there. Take some time, go through, pick out the ones that you're having some trouble with. Again, the regimen looks to be about the same here. In this case, they want you to find the voltage across the capacitor in polar form. Is the circuit predominantly inductive or capacitive? So, in this case, you create your rectangular solution for the vector sum. You do your conversion then into polar. The impedance in the parallel combinations then of R2 and X sub Z, they name it Z sub 2, so that's your impedance in that branch. You're going to go through and calculate them using the polar form. Okay, again, this looks a lot like what you've seen before, the product over the sum, the inverse tangent. So the product over the sum, the difference here is that you've got squared terms and square root terms, and that's going to yield then your solution, 447 at an angle of minus 63.4 in ohms. Okay, once you do that, then you are going to do a conversion here where they have you convert back to the rectangular form. Okay, sometimes that's the easiest way to handle the solutions. It seems tedious, but that's the way that you have to handle them to combine the terms. Okay, so now in this case they're telling you to solve for z total, z1 plus z2. When we're adding, you use your rectangular form, so they've combined them, and then the next step is they convert it right back to polar form. So again, you've got your Pythagorean theorem, your inverse tangent, to get your value then in the 1204 at an angle of 4.76 degrees in ohms. And then finally, they say now apply the voltage divider formula. Again, this is the same relationships that you learned in ET131 to find V sub C. So V sub C is equal to Z2, that branch, okay, and then divide it by the total, multiply it times V sub S. That should be very familiar with you, okay, for you. So you've got your terms here. Again, since we're dealing with a product and a sum here, or a product and a quotient, you use the polar forms because that's the easiest way. You end up with 1.86 at an angle of minus 68.2 in volts. So therefore V sub C is 1.86 volts and lags the source by 68.2. The plus J term in the total impedance or the positive angle in its polar form indicates that the circuit is more inductive than capacitive. However, it's just slightly more inductive because the angle is small. This result may surprise you because X sub C equals X sub L, which is 500 ohms. However, the capacitor is in parallel with a resistor, so the capacitor actually has less effect on the total impedance than does the inductor. So in the diagram below then we can see the phasor relationship of V sub C and the source voltage. Although X sub C equals X sub L, this circuit is not a resonant circuit. It's not in resonance because the J term of the total impedance is not zero due to the parallel combination of the resistor R2 and X sub C. You can see this by noting that the phase angle associated with Z total is 4.76, okay, and not 0. So go through this example. If you have to go through it more than once, do it, because it's rigorous, but it's a very instructive example. Okay, the same thing in the next one. Find the voltage at point B. So we're looking at what is essentially the output taken across the resistor R2. The voltage at B is the voltage across the open output terminals. Use the voltage divider approach. To do so, you must know voltage at point A. So you can see you have to look back into that circuit into point A here first. So you need to find the impedance from point A to ground as a starting point. Okay, the parallel combination of X sub L and R2 then is in series with X sub C. So you can see that right here as you start combining and decomposing the circuit. You can see once you collapse those two, it becomes in series with X sub C. Okay, this combination is in parallel with R1. So again, we're looking back again across point A, in parallel with R1. Call this impedance point A to ground Z sub A. To find Z sub A, take the following steps. The impedance of the parallel combination then is R2 and X sub L, and we call that Z sub 1. Again, this is a very instructive example. Work through it, go through it step by step here. Make sure you understand. Again, it's very tedious in that it has you do rectangular, polar, but that is the essence of how you do an analysis on this type of circuit. And you can see here in figure 1734 how they have reduced everything down and combined the values together to determine the impedance at point A. So at that point, then you can use the voltage divider rule again to find V sub A at point A in the figure. Okay, so they've combined the terms, the ohmic terms here for Z total, and determined the value here for Z total in rectangular form. They convert it then the next step to polar form. Now you have 2.22 at an angle of minus 8.82 degrees in K ohms. So the next step then, voltage at point A, what does that look like? Voltage divider again. So you're using the Z sub A is the point you're looking at or measuring. You're relating it to the total, multiply it times the source, you get the voltage drop. Then looking into that output all the way back to Z sub A after everything has been combined together. Next, find the voltage at point B by dividing V sub A down as indicated in the figure below. So you can see what they've done here in combining terms. So V sub B then is Z1 over Z2. Those are your reduced terms times VA. And in doing so, you get 45.9 at an angle of 54.8 volts. Surprisingly, V sub A is greater than the voltage source, and V sub B is greater than VA. This result is possible because of the out of phase relationship of the reactive voltages. Remember, X sub C and X sub L tend to cancel each other out. So in doing the particular series parallel configurations, then it's important because it represents a circuit having parallel inductors and capacitors in the branches. With the winding resistance, in this case, you see the winding resistance is included for the coil. So it's helpful to view the series parallel circuit to an equivalent parallel form. So you see what they've done here is they've got an inductor equivalent and a resistor equivalent form here so that they can combine the values together. Make note in the over here they give you the Q X sub L by the resistance of the winding. So the equivalent inductance LEQ then is the equivalent parallel resistance, which they call R parallel equivalent, is given in this form. So copy this down in your notebook. The equivalent is equal to L times the Q form that we've already seen. Okay, the resistor parallel equivalent then is the winding resistance multiplied times Q plus 1, where the Q is the quality factor of the coil X sub L by the winding resistance. Derivations of these formulas are quite involved and are not given here. Notice that the equation that for Q greater than 10, the value of L equivalent is approximately the same as the original value of L. For example, L equal to 10 millihenries, Q then is equal to 10. So they run that through the relationship, so you can see LEQ is just a tad higher than the original value. The equivalency of the two circuits means that at a given frequency, when the same voltage value is applied to both circuits, the same total current is in both circuits and the phase angles are the same. Basically, an equivalent circuit simply means circuit analysis more convenient. Okay. Another example here, we've got a capacitor, we've got an inductor with its winding resistance, and a resistor all in parallel. So in this case, solve for the inductive reactance, find Q. Since Q is greater than 10, we can let the equivalent equal to 5 millihenries. The equivalent parallel resistance then becomes, when we take that relationship, our equivalent is the winding resistance Q squared plus 1. We get 10 k ohms for our value for the equivalent. This equivalent resistance appears in parallel with R1 as shown. When combined, they give a total parallel resistance then of 3.2 k ohms. Okay, again, the way to get to this and learn this is go through these examples and learn from them. The next section talks about a non-ideal circuit. Again, you have your relationship for Q. You've got your relationships again for your equivalent circuits. At parallel resonance then, X sub L is equal to approximately X sub C. So your equivalent X sub L is equal to X sub C at parallel resonance.